Welcome to the deep dive. If you spent, any time online recently, you've seen it. Video is just consuming the internet.
Oh, absolutely.
It's something like 80% of all internet bandwidth, and that number is
Yeah.
it's only going up. And for the last couple of years, the whole AI conversation has been just dominated by large language models,
All text all the time.
right, the text generators. But when you actually look under the hood at the infrastructure, generative video, and these diffusion models, they're fundamentally different beasts. So our mission today is to go deep into that technical engine room. We're here to unpack the core technical chasm between optimizing these massive LLMs and the cutting-edge generative media, especially video. We really need to understand why running, say, over 600 specialized models at scale requires a totally unique approach,
To everything.
from the silicon all the way to the software stack. We're talking about a difference in computational demand that really it changes the entire business model.
It's so vital to have this discussion now because, honestly, for a long time, generative media was, well, it was overlooked. If you trace the investment, the talent that moved into AI, it all went to the AGI narrative.
The big language models.
Exactly. The LLM's image and video generation sort of felt like a toy use case. People played with them, but it didn't have that immediate industrial application that LLMs found in, say, customer support or code generation. But that has changed completely. And fast. The models are not toys anymore. They're capable, they're useful, and we're seeing generative media emerge as this massive market with applications that are just so unique and demanding compared to the text world. The technical demands have forced a real reckoning.
And the speed of this evolution is frankly something else. We saw a really compelling source that compared this moment to animation history. Is the former DreamWorks CEO, Jeffrey Katzenberg.
Oh, interesting.
Yeah, he noted that the pushback, even the rebellion against AI today, is a lot like the resistance computer graphics faced decades ago when animation was moving from hand-drawn cells to 3D.
Right, the traditionalists were worried it would kill the art form.
Exactly. The resistance always feels existential, but the lesson, as he points out, is that technology is, ultimately unstoppable. And the pace here is the real story. Sources are showing that the top video models now have a documented half-life of just 30 days.
Just think about that. A 30-day half-life. I mean, for an engineering team trying to build a stable platform, that means whatever optimized architecture you deploy today,
It's obsolete next month.
it's functionally obsolete or massively outperformed in a month or two. That puts just enormous pressure on the infrastructure, forcing platform teams to constantly iterate and find efficiencies that the foundational labs themselves, they haven't even gotten around to optimizing yet.
And that speed, I imagine, leads directly to the sheer variety of models we're seeing. Everyone kind of dreams of that one big omni model
Right, the one model to rule them all.
that does text, video, image flawlessly. But that's not the reality, is it?
Not at all. It's a nice theory, the Omni model. But in practice, you get much better, more controllable, higher fidelity results by optimizing for a specific task. You might have one model that's just for upscaling, another for detailed architectural textures, or one engineered just for, say, fluid simulation. And that creates an immediate infrastructure challenge. You can't just rely on one or two big models. Our sources cite that a high-performance system has to manage, load, and run over 600 different active models simultaneously.
600.
And here's the really fascinating part. The platform, the infrastructure, has to be so good at this dynamic optimization that it has to run those models faster and more efficiently than the labs that actually created them. That's the only way to be economically viable.
Okay, so that brings us to the core technical device. Let's get into it. When we talk about optimizing LLMs, the constraint you always hear about is memory bandwidth. Can you just define what that means at the hardware level? Why is it the main bottleneck for a GPT or a Claude?
Absolutely. The LLM challenge is, at its heart, a data movement problem. You have a massive model, right? Hundreds of billions of parameters. And when you're doing inference, you're just predicting the next single token in a sentence.
The next word.
The next word. To do that, the system has to go get this colossal file of model weights from its main memory, your DRAM, and move those weights to the super fast local memory right on the chip, the SRAM. That's where the math happens.
And the file's just too big.
The weights are so massive that the bottleneck is almost never the calculation speed. The GPU is incredibly fast. The constraint is the pipe, carrying that data. You're constantly limited by how fast you can shuttle those giant parameter sets from DRAM to SRAM. You're waiting for memory bandwidth.
So LLM optimization is all about compression, shrinking those files to move them faster.
Exactly. Clever tricks like quantization, compression, anything to shrink the files and minimize that memory movement time.
Okay, so that's memory movement. But generative video diffusion models, you're saying it's a completely different physics problem. They're compute bound.
Precisely. We move from a memory movement problem to a raw computation saturation problem. Diffusion models work very differently. Instead of predicting one token from a huge weight file, they're denoising a blank canvas. They're operating on thousands, even tens of thousands of tokens at the same time across a whole image or a video frame.
And this denoising, it involves something called attention.
Right, it has to perform what's called attention over all those thousands of tokens, constantly analyzing the relationships between different parts of the image to figure out what color or detail comes next. And here's the kicker. That whole denoising step has to be repeated dozens of times.
Dozens.
Often 50 times or more to get from pure noise to a clean, high-fidelity output.
50 times. That seems incredibly inefficient.
It is, but it's necessary for quality.
Oh.
And because of that repeated, high-volume calculation, 50 layers of computation across thousands of tokens, these models completely saturate all the compute bandwidth of the GPUs. They're doing so many floating point operations that they become compute bound.
So the optimization strategy has to shift.
It shifts entirely. You stop worrying so much about shrinking the weight files and start worrying about finding the most efficient, custom-written ways to execute around the GPU core itself, to use every single clock cycle of its power.
Okay, let's put some numbers on this. I think quantifying this disparity is where it really hits home. Let's take a standard 200-token LLM prompt, a pretty typical request, and call that our baseline unit of measurement, so 1x of compute.
Okay, 1x.
How does that scale up when we move to visuals?
The jump it's immediate. Just generating one single high-quality image is already around 100 times that LLM compute cost.
So 100x just for one static frame.
Right. You've gone from 1x to 100x instantly. But the real chasm, the real shock, is video. If you're generating a standard def 5-second video at 24 frames per second, that's 120 frames, that one request takes an astonishing 10,000 times the compute of that initial LLM prompt.
10,000x.
10,000x. You've gone from predicting one word to calculating 50 layers of denoising across 120 complex images. The cost curve is it's exponential.
And what if a customer wants professional grade, like 4K?
If you push that up to 4K resolution, you can add another 10x multiplier on top of the 10,000x. So now you're well into the 100,000x range for just a few seconds of high-fidelity video.
So this isn't a problem you just solve by throwing a few more GPUs at it. This needs, like you said, compiler magic.
Absolutely. The intuition behind that cost, it traces right back to those 50 repeated denoising steps. If you scaled a video model up to the same parameter size as the biggest LLMs, the cost would be ruinously expensive. That single video demands 50 iterations of attention over 100,000 tokens. That insatiable demand for raw computational power is what drives the need for this hyper-specialized optimization. You literally cannot afford to waste a single operation.
That 10,000x disparity, it's not just a metric, it's an existential challenge. If the compute is that expensive, the only way forward is through radical optimization.
Yeah. So what are the nuclear options here? How do you get this kind of speed, especially when the models change every 30 days? The top teams are all in on compiler-level optimization, and specifically a technique called templated kernels. A kernel, you can think of it like a very specific hand-tuned recipe for one calculation on the GPU.
Okay.
The process uses a tracing compiler that just watches the model run. It recognizes common patterns, like a specific sequence of matrix multiplications that happens thousands of times. And the engineers create these generalized templated kernels.
Oh, like a blueprint.
Exactly, like a blueprint. You can think of it like having the main structure of a cake recipe. The ingredients and mixing process are 95% done. When the compiler sees a new model needs that type of operation, it just swaps in a hyper-optimized, specialized version of that kernel at runtime. It's like having a compiler that can instantly substitute a generic operation with a hand-tuned recipe that runs way, way faster on that exact hardware.
So instead of trying to rebuild from scratch every month for 600 models, you're optimizing the common building blocks, the kernels that can be deployed across everything.
Precisely. It lets them maintain leading performance even when a new foundational model just drops out of nowhere. If you had to wait 6 months for the official optimizations from the model creators, you'd be out of business.
And this isn't just happening on one GPU. You called it distributed supercomputing. What does that orchestration look like across, say, dozens of data centers?
The scale is immense. You're managing a GPU cluster that might be spread across 35 different data centers around the world. And that creates a whole new layer of complexity on top of the kernel optimization.
Right.
The infrastructure has to handle loading and unloading those 600 plus models efficiently. It needs smart routing. When a customer makes a request, you have to route it to the exact GPUs that already have a warm cache of the models they need.
The ones they just
They're
used.
the ones they use moments before. If you send it to a cold GPU, you instantly add minutes of latency.
Yeah.
And for a professional creative workflow, that's just unacceptable. It's a monumental orchestration problem.
Let's shift up from the plumbing to the application layer.
Hmm.
In the text world, we're seeing consolidation, right? A few big monolithic LLMs are dominating. But you're saying the visual world has this thriving, diverse, long tail of models. Why is the workflow so different?
It's because visual tasks are inherently subjective. They're aesthetic. A customer support chatbot, you want it to be consistent and objective. A visual artist is looking for a unique style, so you need models with different personalities.
Right.
One model might be amazing at rendering metallic textures, another excels at stylized smoke or water, and a third might be built just for editing text inside a generated image.
And that drives complexity. You mentioned a typical high-volume customer uses something like 14 different models.
Routinely, around 14 different models at the same time, often chained together in these complex multi-stage processes.
Can you just walk us through an example? What does a 14-model chain even look like?
Sure, it's usually a pipeline. A customer might start with a text-to-image model for a rough concept. Then they'll send that image to a refiner model to add detail, then an upscaler to increase the resolution. That high-res image might then go to a spiralized motion model to animate it, then a stylization model for a visual filter, and finally a cleanup model to fix any artifacts.
Wow, okay.
That's 5 or 6 models for one step, and they'll run that process iteratively, maybe swapping out a couple of the core models to test different looks, and they easily hit that 14 model count.
And you said professional teams actually prefer open source here, which seems counterintuitive. In the LLM world, it's all about proprietary black boxes. Why would a studio choose open source?
Control. It's all about control, which is the lifeblood of creative work. They're trying to match a specific brand aesthetic or a cinematic style. With an open source model, they can go in and replace small pieces of it. They can fine-tune it to steer the output and guarantee it matches their vision.
You can't do that with a black box.
You can't. That ability to custom tune the personality of the output is essential for creative work. A generic chatbot just doesn't need that.
It's so interesting how the generative workflow is now mirroring traditional pre-production.
It's a direct parallel. The most common pro workflow now is to iterate on the visuals with an image model first. They create a whole storyboard of high-quality, concept-accurate images. Then, and only then, do they use the super expensive video models to animate between those approved images. It's the exact same planning process, just at lightning speed.
Looking at market impact, I'm really excited about the potential here for content that was just too expensive or niche before. Education, for example, feels almost untouched by this.
The examples are starting to get really compelling. We're seeing adaptive security training where the scenarios are generated on the fly. And there's the Faith Bible Story app, which uses generative video to create thousands of short narrative clips. It shows you how to reach an audience with personalized, engaging content at a cost that was impossible 5 years ago.
And what about old media, Hollywood? Are they still in revolt or are they getting on board?
They're moving from revolt to acceptance, just like Katzenberg predicted. The big IP holders are engaging seriously now because they have 3 things AI startups don't: the IP, the budget, and critically, the storytelling and filmmaking know-how. This is a tool, and their expertise in narrative gives them a huge advantage.
That makes sense.
That said, we're seeing new, purely AI-generated IP rise up, like those Italian railroad characters that just kind of came out of the internet zeitgeist. And look at ads. Programmatic ads are using this heavily, going from basic UGC style to high-production, custom-fit ads on the fly, like that Coca-Cola example.
So zooming out on all this, the key takeaway really is that the extreme computational demand of generative media, that 10,000x cost disparity, isn't just an inefficiency. It's an architectural imperative. It forces a completely different optimization strategy focused on raw compute, driving this need for hyper-specialized infrastructure.
Exactly. And that extreme compute cost dictates the timeline for what's possible. I mean, feature-grade short films, maybe under 20 minutes. With some smart human editing, that's probably feasible in less than a year. But fully generated AAA quality games, that's likely 3 to 4 years away, just because the computational lift is so much higher. So here's a final provocative thought for you to explore. If model quality keeps improving and generation time falls to near real time, allowing for, say, on-demand 4K video rendering, what's the biggest bottleneck left? Is it a lack of R&D breakthroughs in the models themselves, or is it simply an overwhelming, persistent shortage of the physical hardware capacity needed to meet that infinite 10,000x plus demand? The compute chasm never seems to truly close.
That's a fascinating question. Are we waiting for better algorithms or just more chips? Thank you for this deep dive into the engine room of generative media. We'll catch you next time.